Great, thank you. So I'll start off by saying that I really am happy to be able to present this work today and to, in general, be working on New Horizons data because this is a really awesome data set and has given us the capability to look at KBOs in ways never before possible. New Horizons has taken advantage of its place in the outer solar system to do these high phase observations of objects in the Kuiper belt. Voyager did not observe any objects in the Kuiper belt as it flew through because we didn't even know that the place existed yet. So this has really been a pleasure to work on throughout the years. So New Horizons entered this era of high phase observations of Kuiper Belt objects not long after it launched. The very first observations of dwarf planets were in October of 2007. So that started the ball rolling, and we've been looking at other Kuiper Belt objects since then through every phase of the mission from prime, the first extended and second mission extension. So as New Horizons is NASA's observatory in the Kuiper Belt, what we like to look at here is these objects at high phase angles. The phase angle is the angle between that spacecraft, the target, and the sun. And what this lets us do is accomplish many tasks. One of those would be searching for binarity, satellite discoveries, which New Horizons has done. Also enables measuring rotation curves, light curves at multiple high solar phase angles, and that can help determine what the period sizes, poles, and shapes are. We get these solar phase curves that help us characterize surface microphysical properties. And we get also astrometry, good indications of where those objects are in their orbits, which help with predicting Earth-based occultation observations, which can also get you the shapes and sizes and albedos. But this talk is going to focus mainly on the solar phase curve aspect. So this is an inventory of objects that New Horizons has looked at. New Horizons has observed objects from every dynamical class of KBOs, many cold classicals, because we flew right through the dense part of the belt, of course. Hot classicals as well, objects from the scattered disk, resonant objects, larger TNOs, and a couple of centaurs. This presentation will focus on the larger objects, the large TNOs, and the dwarf planets Eris, Makemake, and Haumea. You may recognize or not recognize the name here, Mani. Just last month, that was the new name assigned to, or the name assigned to 2002 MS4. So MS4 now has a name and it's called Mani. And yay, it's pronounceable. So here is an example of a whole disk integrated solar phase curve. This is the reflectance versus solar phase angle, and it is diagnostic of surface regolith properties. It may look here, or all these points do follow the same curve, but as you'll soon see from many of these Kuiper belt objects, they are distinct. They don't all follow on the same curve. But from modeling this variation in reflectance with phase angle, you can determine regolith properties such as the porosity, directional reflectance, whether particles scatter preferentially forward or backward, particle opacity, crystal structure, whether they're euhedral, well-formed crystals or not anhedral. The roughness can be evaluated, but really you get better roughness measurements from disk resolved observations like you have with a flyby. We get that from the entire Pluto system and then Arakoth, of course, but the other objects are observed as point sources only. So you can gauge the roughness, but not constrain it well. One thing that we do have to deal with, though, even though these spacecraft observations are unique and extremely valuable, they happen to be sparse. So we don't have well-sampled phase curves like the one here. This is put together by all the cold classicals. Each dot corresponds to a different color. So if you look at one color, there aren't a lot of points of that one color. And that sparse non-uniform sampling does present modeling challenges. So in order to model these phase curves well, it's best to have observations at all phase angles, but the extremes are really important. So as New Horizons approached the Pluto system, it did so at a phase angle of 15 degrees, and the phase angle increased from there. So it never got to see the Pluto system at the small phase angles. Like some spacecraft we had, the Hayabusas did observe their own shadows on Itokawa, asteroids Itokawa and Ryugu. And that enables measurement of the opposition effect, which is this brightening of the surface that you see here. So this is a feature of the regolith particles. It is not an intrinsic albedo spot that you're seeing there. If, in fact, if you were to follow the spacecraft across and follow that shadow across the surface, you'd see that bright spot move with the spacecraft. It is due to two phenomena: shadow hiding. Particles hide their own shadows. That's a geometric phenomenon, and then a coherent backscatter phenomenon, which is constructive interference of rays as they interact with the surface. So the minimum phase angle that you can observe an object at is defined by the angular size of the sun seen from that object, which for the KBOs is great because they're so far away from the sun. The sun is so much smaller out there. We have much more access to that region of the phase curve. For Pluto, very conveniently, Pluto crossed its line of nodes in 2018, so not long after the New Horizons encounter, and that gave us access to the smallest phase angles for the whole Pluto system. In 2018, that happened, and at the time of opposition, the non-encounter hemisphere of Pluto was visible, but in 2019, at the following year, when the system was at opposition, the smaller phase angles were still visible of the encounter hemispheres. And we will not be able to do this again until 2179. So it's going to be a long wait to look at this system from Earth at phase angles this small. So when we model the solar phase curves, we can use empirical analytical equations like the HG magnitude system is often used to model asteroid phase curves, but these don't relate parameters to physical regolith properties. You can use numerical physically based models. You can use analytic physically based models, and one of those would be the Hapke model, which is commonly used and been referred to several times during this meeting already. The Hapke model is based on radiative transfer. The parameters are related to physical regolith properties, but there are issues with non-uniqueness that can arise from having so many parameters. So here's where I bore you with the math. This is the Hapke equation. The model is used to predict the spectrophotometric reflectance behavior at all photometric geometries and to characterize the microstructural and thermophysical properties of the regolith. As you can see, there are a lot of parameters involved here. There are major obstacles to accomplishing that second goal. The sparsity and non-uniformity of the phase angle coverage is one of those. There are so many parameters, and the parameters themselves can be coupled. So they also have the ability to mimic each other. There are systematic differences in the measurement uncertainties then that you get between the data collected by different instruments as well. And all of that folds into establishing what the true uncertainties are on each parameter. So Paul Helfenstein and I put together a paper that addresses these. He's the lead author. It came out in June in PSJ. This is the direct reference to that paper, where we apply this strategy to the New Horizons KBO phase curves that we published in 2022, so a few years back with the New Horizons data. So fitting the Hapke model to these phase curves, we find a set of parameters that minimizes the chi-squared and come up with a minimum residual. An example here is shown for the KBO 2002 KX14, which some of you may recognize. It's a typically classical KBO, which occupies a space just inside the cold classical belt. We have Earth-based observations those are the ones at the lower phase angles, but then with Lori, we just have the one point at about 70 degrees. So that's a challenging phase curve to fit with a handful of Earth-based observations at phase angles no larger than a degree and a half or so, and then one more point at 70 degrees. So what do you do with that? So this paper addresses how you fit a phase curve like that. And it develops exclusion criteria to address the non-uniqueness portions. The single particle phase function can mimic the opposition effect. The two opposition effects, the shadow hiding and the coherent backscatter, can mimic each other. The macroscopic roughness can even mimic the shadow hiding. It's a complicated situation. So what we developed was what we call an effective geometry constraint. And that measures the sensitivity of each parameter to the range of available phase angle coverage. And that determines which ones need to be fixed in your fits and which one fixed to assumed values, because they're too unconstrained by the phase angle coverage that you have. And I give the mathematical expressions for the effective geometry constraint. So here are the solar phase curves of large KBOs and dwarf planets. This is what we published in 2002. And these grouped into three different areas, what should be obvious at first is that they don't, they're diverse. They're not all on the same curve. The objects that have volatile surfaces are shown in red. The ones that have spectra dominated by water ice are in blue, and the ones without either of those things are shown in black and are much steeper. So the hypervolatile surfaces have much shallower phase curves. At the near opposition point, we still see a lot of diversity in the shapes of these curves. I've put the hypervolatile surfaces up on this plot, and the other ones are below, and then everything is together on the plot in the middle. They're all normalized to zero at zero phase angle to facilitate the shape comparison. In a recent paper, Hapke related the angular width of the coherent backscatter shadowing effect to the surface maturity. And that is what is shown over here on the right. The maturity increases to the right and is the lowest for Pluto and Triton with these very narrow opposition surges, not very high in amplitude, nowhere near as high as Charon, but very, very narrow. So those surfaces have, of all these objects that we looked at, the lowest maturity, their youngest. And next to that is Charon, is also possibly a very young surface. To compare these phase curve shapes with other objects in the solar system, I look at the phase integral, which is basically the area under the phase curve. So shallower things are going to be up here with high phase integrals and plotting versus their geometric albedo. So compared to other bright objects in the solar system, satellites of the giant planets, the phase curves of the dwarf planets are distinct. They are not the same as the bright satellites of Saturn and also the satellites of Jupiter. And you can compare the other darker ones in here mixed in with the Uranian satellites. And we've been mentioning the bond albedo of Eris that has been revised in this June 2025 paper. Here's a direct reference to it in the table with all the bond albedos, phase integrals, and geometric albedos for all these TNOs. And I will put my summary slide up. You can read that. And we'll take questions if there's time for one.
Yeah,
Thanks.
awesome. Thanks, Anne. All right, we have time for one quick question. If someone wants to run to the mic, Leslie is doing so.
Okay, I've got two questions, but we can go back and forth between Young's. The first is for the using the phase curve to get the bond albedo. the opposition surge so fascinating from a physical point of view, but you can ignore that last little opposition surge for the purpose of calculating the bond albedo. So my question is, uh, if you normalize instead of at 0 degrees at something outside that surge, like 10 degrees, do you see the same clustering, or does the clustering reshuffle itself?
Very excellent question. That is something that I can take a quantitative look at, but it is something that I should look at further. Some of these, for objects that have very similar opposition surges, it's not going to matter that much, but I'm thinking of Sharon, which has the huge one. It could make a difference there. Yeah.
Thanks.
Hi, Ann. This is a go back to Jason's talk. He's sitting right there, though, so I thought that I would ask, when Jason showed the terrain on Pluto that was dark, neutral, and bright at different angles, it looked to me like he was showing a phase function that had kind of a really broad forward scattering part and then a really sharp back scattering. But maybe I read the the x-axis wrong. I was wondering if you remember that and if you had thoughts on what's going on Pluto. Or you
That was there's an atmosphere in there as well. That's why. Let's talk about that offline just
Okay,
for time's sake.
thanks. Never mind.
Yeah,
Oh.
the atmosphere is going to have a very strong forward scattering component at very high phase angles.
We've run out of time, so maybe you can catch Anne in the break to ask the
Okay.
other questions. Sorry, Paul.
Great.
Sorry, Leslie.
Great talk. Thanks.
Thanks, Ann.